Hello everyone! In this video, we discuss two very important ensemble learning methods when working with decision trees, random forest and gradient boosting. In order to understand the differences between these two methods, we're going to first explain the basics of ensemble learning and discuss bagging versus boosting. And then we will go through some algorithmic and implementation aspects of these two methods. So what is ensemble learning? The goal of ensemble learning is to combine multiple base models. We also call these usually weak learners to improve overall performance. So this means that if I have model 1, which is not great on its own, and I have model 2, model 3, and 4, and so on, that these models may not perform very well on their own, but if we combine them together, then the combined model may have much better performance compared to the individual ones. And there are two very popular ensemble learning techniques. One is known as bagging, which stands for Bootstrap Aggregating. And then the second one is boosting. So what's the difference between these two? In simple terms, bagging builds multiple independent models. And these models are built in parallel. And the idea is to use bootstrapped or resampled datasets. So here usually the implementation is very simple because we build these models independently using bootstrap or resampled datasets, and then we average their predictions or aggregate their predictions. However, boosting is a little bit more complicated because in boosting, we build models sequentially, where each new model focuses on improving the performance of the previous ones, or in other words, we try to correct the errors of the previous models. And both of these, they aim to improve performance by reducing usually the variance and as well as the bias of machine learning models. And something here I want to focus is that when we talk about bagging and boosting, you can apply this to any machine learning model. However, in this video and in many cases, we talk about decision trees. And these decision trees are the building blocks or those base models that we combine them together either independently or sequentially, depending on whether we use bagging or boosting. And again, the goal is that to have something that is better than one decision tree. So as a very quick reminder of what a decision tree is, so we have this tree structure where at each node, starting with root node, we're going to split features. And let's say here we have this synthetic data set where I created this nonlinear function, which is actually the sine of x, and I added some random noise to make this even more interesting. So now if we fit a decision tree of depth 2, so I have to correct this because this is a depth 2 prediction, you can see that we have two levels. This is level 1, this is level 2. So what's happening here is that first we're going to look at this condition, whether the input feature x is less than or equal to 3.186 or not. If this is true, we come to this node. This is usually known as the intermediate node. And now since we put the max depth to be 2, means that we're going to have another split if necessary. And this gives us again two conditions, true or false. And the same thing happens if this original condition is false. Then we're going to again have true and false. And this means that eventually we end up with 2 to the power of 2 or 4 predicted values. So each leaf node here, it gives us one predicted value. For example, here is 0.687, which is what we have here, then 0.231, and then the two negative values that we have here. So you can see in this case, decision tree is this nice tree structure which splits this input feature and gives us this information about the fact that all the data points that they end up in this leaf node, they have this predicted value, these ones they have this predicted value. And the way that we do this, I explained this in the previous video, is using the idea of impurity. meaning that when we want to do data splits, we want to decrease the impurity that we have in our nodes. And the data points that are inside one node, they should be as homogeneous as possible, which in the case of regression, it means that you want to have like output values that are as close as possible to each other. And for classification, we use what is known as the Gini impurity score. So we saw that in the previous slide, decision tree with depth 2 didn't provide a very nice approximation because we have these lines that they are basically like horizontal lines, and we have 4 of them. So it does not really capture this sine function that we have here. So the idea is that, well, let's increase the depth of this decision tree. So now we can find more complicated prediction functions. And if we do this, we see that yes, we can now get a much better, or I would say finer approximation of this sine function. However, we run to a very classical problem. So you can see that when I added this noise to this data set, now this prediction function that we have is going through all these training data points, including the noise that we added here. And therefore, this prediction function, this red one here, is we call it as too wiggly, which means that it's going to overfit or have very high variance, which means that it's going to have poor generalization on new or unseen data. So this high variance is really a significant problem, and we have to find a way to make this smoother. So one of the things that we can do is to use this method, which is called bagging, right? Bootstrap aggregating. So how does this work? This is very simple. We have a training data set, and the training data set here is supervised learning. We have input and output pairs. And we have to set the number of bootstrap models. And here I assume that, for example, this B is equal to 100. That's the default when you're looking at the implementation of bagging for decision trees, which is known as random forest. And then for each case, and I show this by small b, going from 1 through this uppercase B, so let's say b equals 1 to 100, we're going to create a bootstrap data set. And this simply means that when we have n data points, we're going to use sampling with replacement. So in the bootstrap data set, we may have multiple versions of a data point, and we may not have some data points. This is one way of perturbing a data set. And then we're going to train a base model, in this case a decision tree like what you saw in the previous slide, to this bootstrap dataset. And eventually, when we wanted to make predictions, we're going to send our input data or new data into each function. And then if it's regression, we're going to find the average output. If it's classification, we can look at, for example, majority votes, right? See which class has the highest number of occurrences in these B models that we have. But right now we are mainly focusing on regression models because I do believe it's easier to understand the main concepts behind bagging and boosting. And one, I would say also another thing that we have to discuss when we talk about random forest. So yes, random forest is based on bagging, which means that you're using these bootstrap data sets. But also we can use a small trick to make sure that the trees that we're going to independently train are as sort of like independent as possible or decorrelated. And that's the fact that when we want to do these feature splits, we can technically consider all the possible features to see which one gives us the best reduction in impurity score. However, it is very common to use some sort of like randomness, meaning that instead of looking at the entire set of features, we can look at a small subset and only look for the best split according to that selected subset of features. And in the case of classification or regression, you can see one heuristic method is to set the number of features considered at each split to be the square root of total number of features, for example. And again, the whole idea here is just to make sure that the trees that we independently train are as uncorrelated as possible. And here on the left side, you can see that the decision tree with max depth 10. On the right side, you can see the random forest which you can see that it's much smoother than what we have on the left side. So this means that we can successfully control the variance of our ensemble model, in this case random forest, to make sure that we have better generalization performance. And if you're wondering, in this case, I'm setting the number of estimators in scikit-learn's implementation to be 100. That's a very typical value for the number of ensembles. Although random forests are very popular in general, an immediate concern is that we lose a little bit of interpretability. And why is that? Because when we are working with random forests, we have an ensemble of trees, and so we cannot just look at one tree structure to decide how different features lead to the predicted values that we get. And the good news is that there's actually a way to get around this problem, and that's by looking at this metric, which is called mean decrease impurity. So what does this do? So MDI averages the impurity reduction attributed to each feature across all the trees that we have in our forest. So this means that in tree 1, we may have at one node, one feature reduce the impurity, either in terms of a squared error or in terms of gene impurity, let's say by some number. And that same feature did this thing, for example, by another number in the second tree and then in the third tree. And then so we can take the average across all the trees. So this means that this feature on average reduces impurity, which is again very important when you're working with decision trees, because you want to have pure nodes at the end. And you get this number that shows the importance of each feature and its contribution to the final prediction of a random forest. So in a previous video, we talked about, for example, SHAP method, which is another way of explainable AI, but there are different ways of defining contribution. So one way of defining contribution when you talk about decision trees is how much you decrease impurity based on a feature split. And let's see how this works. So let's say in this case, we work with the low diabetes data set, which is from scikit-learn. It's a great data set which shows the progression of diabetes based on some clinical features. And in this case, what we have done is that we have trained a random forest regressor using this data set. And then we look at the feature importances. And this is something you directly get from scikit-learn. And the nice thing is that now, on the y-axis, you can see we have this importance score, which is the mean decrease in impurity. And on the x-axis, we have these sorted from the highest to the smallest. So this means that in this specific problem, it appears that BMI, or body mass index, has one of the highest impact or contribution to the progression of diabetes. And then there are also, for example, BP here, which stands for blood pressure. And then we have some also blood measurements that you can find this information in the description part of this low diabetes. So overall, as you can see here, when you're working with random forests, still you can have an interpretable model based on this idea of mean decrease in impurity. So next, let's talk about the second type of ensemble learning, which is boosting. So very much like bagging, the idea of boosting is to just have an ensemble of multiple machine learning models that they hopefully perform better as all together rather than working with individual models. However, unlike bagging, boosting trains models sequentially, not in parallel or not independently. And this is a very critical differentiation between the two. And the idea is relatively simple. At each step of boosting, a new model is trained to fix the problems of the previous models. Right, so this means that if we have, for example, regression problem, which is again one of the, I think, easiest ways of understanding random forest and also boosting, we can think of prediction errors as residuals, true values, output values minus predicted output values. So at each time or at each step, we have a model that makes some predictions and we have a prediction error or residual. And our goal is to find a new model that can fit to this residual. So try to reduce that as much as possible. And then this new tree or this new model is added to the existing model once we find it, and the residuals are updated. So here we have the general algorithm for boosting. And this is mainly for regression. Obviously, you can make a few changes here and there to make this also work for classification. So we first set the initial prediction model to be 0, meaning that we don't predict anything. This is our kind of like step 0. And then we set the residuals for all the training points to be the actual outputs, because right now we have not predicted anything. So our residuals are basically the true outputs. But I will tell you exactly why we do this, these RIs, these residuals, why we define it like this, because then we go through these B steps of boosting here. You can see that we fit a regression tree. And also here we can put a maximum on the number of splits, because the idea with boosting is that you want to have very, very simple base models. That's why you can say that, okay, I want to have this maximum number of splits for each individual model. And we fit this tree to the residual and the training data. So this means that instead of working with X and Y, we are working with X and R here is the residual. So the very first time that we go through this for loop, R is also Y. So this means that we are really finding a model that fits to the inputs and also true outputs. However, this is going to be different the second time we go through this for loop, because in that case, we already have predicted part of the output and we have some residual, and now we want to fit our decision tree to this residual. And you can see this additive model. So we have already some current model. We use this lambda, which is known as the learning rate. So this controls how much each tree contributes to the final model. And then we have this sort of like, the model that we found in this iteration of this for loop. And don't forget that you have to also update your residuals. So meaning that subtract the part of this residual that we have predicted, and that's what this part is. So we get the current residual, we subtract the part that we predicted, and we update this. And then we go through a step A. So now again we update our training data. The X or input features are fixed, but the R, which is the residual, changes every iteration of this for loop. And then we try to find a new tree that fits into that new training data set, and we find this updated model. Again, we use this learning rate lambda to update the entire model that we have, and also we update our residuals. And if it's a regression model, it's very simple, because at the end we can just add all these models together, and this is why it's known as additive model. So if you look at the title of this video is about gradient boosting. So this is boosting, but what happened to the gradient part? So it seems that it's a very simple idea. So gradient boosting, we need to find the residuals. That's like the key thing there. And we can do this easily with like the squared error or the regression models, right? Because that's just simply true value minus predicted value at each step. However, it's really nice if we can extend this to other loss functions and other problems. And that's the main idea of gradient boosting, that we can apply this boosting technique to any differentiable loss function. And this means that loss functions that we can find their derivatives. That's what it means, differentiable here. And this takes us to something called a pseudo-residual. So what is a pseudo-residual? This means that in order to find the residual in a fast way for any loss function, not just the squared loss, you can find the derivative of the loss function with respect to its predicted value and calculate that for the model that we have already found. And also we have a negative sign that we have to consider here. So why is the negative sign? Because we know that the gradient of the loss function points towards the steepest ascent. But we actually want to go to the opposite side. It's very similar to like the idea of gradient descent. We want to go to the direction of a steepest descent. And that's why we have to use this negative sign. And one more way to understand why this formula here works, and also this negative sign, is that think about it this way, that if this loss function, this L here, is the squared or quadratic loss, then this is just simply yi minus predicted value a square, and I use this 1/2 because this is just a constant. We can always consider any constant we want for a loss function. That does not change the empirical risk minimization problem. And you can see that if we take the derivative of these, right, in this case, we have this negative sign, which is here, and then we get 2 times 1 over 2, which is 1, and then we have yi minus f hat xi. And also, since we are taking the partial derivative with respect to f hat xi, there's another negative sign that we have to consider when using the chain rule. So that's why you can see it's very important to consider this negative sign here. So now this cancels this negative sign that we get from the partial derivative. And this tells us this pseudo-residual, or in this case it's actually residual, is this true value minus predicted value. But the nice thing is that you can use this same technique for any differentiable loss function. If you look at circular, you can use this with the squared error. You can use this with the Huber loss, which is the combination of the L1 and L2 losses. So it gives you a lot of flexibility. So how does this work in practice? So gradient boosting regressor, which is the name of this implementation of gradient boosting in scikit-learn, is applied in this case to that sign problem that we had before, right? So this is the blue curve here is the true function we're trying to approximate. We obviously added some noise to the training data to make this more interesting. So now what we have done is to look at this in a macroscopic level, right? So we look at the case when we only have one tree, and then we look at 5, 10, up to 100 trees, right? Because we build these models sequentially. And you can see when we have our first model, this is kind of boring because it almost looks like a constant function. And that's what we expect, right? Because we have a tree that kind of explains the data, but still we have high residuals, right? So you can see in this case, if I deduct, for example, the value at here to the true value, we have a very, noticeable residual. But that is okay because that's the idea behind boosting, right? We don't want to just have one model. We want to have one simple model, and then the second model wants to make the prediction error smaller. And so you can see that if we now, for example, have 5 trees, we have done a much better job in terms of reducing the residuals, which are here, like, just the prediction errors or true values minus predicted values. And if we continue doing these, so going to 25, 50, 100, you can see eventually we can find very nice models that they can fit this training data and approximate the true function that we have. So here's kind of like the main difference between the random forest method and gradient boosting. If you want something very simple to just be able to build multiple models independently and take the average to reduce variance, obviously random forest is a really good ensemble model. However, if you really want to have a model that gives you this flexibility to gradually improve the performance as you have more and more base models, and in this case decision trees, you can see that you get these really nice sort of like models, or in this case representations, that they show you how you gradually can improve these base machine learning models by combining them together. And in fact, boosting models are getting very, very popular these days. For example, you hear methods such as like XGBoost, and so on, and these are getting very, very powerful. But the idea is very simple. We use a base model, we find these prediction errors or residuals, and then the future models, they try to make that residual smaller to the degree possible. And you can control or monitor the performance of these models as you add more and more base models. I hope you found this video helpful.